Hi viewers, welcome to SG Know How channel. We are back with another technical content from pixels to prediction, the role of CNN. Let's have an introduction to computer vision and the role of CNNs in computer vision. Welcome back to the digital age where vast amounts of visual data are integral to our daily lives. In this exploration, we will unravel the journey from pixels to predictions and delve into the crucial role convolutional neural networks (CNNs) play in this transformative process. The significance of visual data in our information rich environment is undeniable, with social media, surveillance, medical imaging, and autonomous systems generating an unprecedented volume of images and videos. Understanding and extracting meaningful insights from this visual data have become paramount. We will uncover the journey from pixels to predictions, highlighting the pivotal role of CNNs. Visual data from social media to medical imaging saturates our information rich world. Extracting insights from this abundance is now a paramount challenge met by the transformative capabilities of CNNs. Join us as we navigate through the significance and impact of visual data in the era of artificial intelligence. Let's dive into the realm of computer vision. Computer vision empowers machines to interpret and comprehend visual information from the world around us. Simply put, it's the art of enabling machines to understand visual information. This encompasses various tasks such as image recognition, where machines learn to identify patterns, object detection, which enables machines to identify and locate specific objects within an image or video, and scene understanding, which provides machines with the ability to comprehend and interpret the overall content and context of a scene. Figure 1, 2 and 3 shows image recognition, object detection and scene understanding respectively. Let's see the significance of computer vision in image processing and analysis. Computer vision plays a pivotal role in automating tasks traditionally handled by human vision. In the realm of computer vision, automation takes center stage, transforming tasks once reliant on human vision. Let's see the features which enables this efficiency and speed. Computers can analyze visual information much faster than humans. It helps in decision making or processing large amounts of visual data in real time. While we human beings are intelligent, computers are computationally faster. A feature which combines intelligence and the speed is nothing but artificial intelligence, and computer vision is the initial part of artificial intelligence. Accuracy and precision. Achieving unparalleled accuracy, computers provide consistent results without human variability. To achieve unparalleled accuracy and precision, computers deliver consistent results without the variability which is inherent in human vision. Non-stop operations. Operating tirelessly 24/7 without succumbing to fatigue, boredom or distractions, computers excel in tasks demanding continuous attention. So we know we will not be able to work 24/7 while machines can work 24/7 without getting tired or fatigue. Automation of repetitive tasks. By automating repetitive tasks, computer vision enhances productivity and job satisfaction. Let's see the role of CNN in image processing and analysis. CNNs play an important role in data analysis and pattern recognition. It can process and analyze vast amounts of visual data, identifying patterns and trends that may not be immediately apparent to human observers. This proves crucial, particularly in healthcare applications. Next is object detection and recognition, which involves identifying and classifying objects even in complex and cluttered environments. Example: autonomous vehicles, surveillance, and robotics. Excelling in complex environments, CNNs identify and classify objects impacting fields such as autonomous vehicles, surveillance, and robotics. Quality control and inspection. In manufacturing processes, it can detect defects, ensure product consistency, and maintain high standards of quality. So, in manufacturing, CNNs detect defects, maintain product consistency, and uphold high standards of quality. Next, it acts as an aid to human decision making. For example, in medical imaging with computer aided diagnostics, it can help healthcare professionals in diagnosing diseases. So, in medical imaging, CNNs aid professionals through computer aided diagnostics, revolutionizing disease diagnosis. In addition, CNNs are helpful in enhancing accessibility and in innovation and research. It acts as an aid to individuals with disabilities. Contributing to accessibility, CNNs assist individuals with disabilities in navigation, object recognition, and text to speech systems. In innovation and research, it helps in innovation in various fields from augmented reality and virtual reality to robotics and automation. Driving innovation in augmented reality, virtual reality, robotics, and automation, CNNs play a crucial role in various research fields. This is a transformative impact of CNNs, expanding the horizons of image processing and analysis across various domains. Having seen about computer vision, its significance, and the role of CNN in image processing and analysis, let's see how the convolutional neural network is unique from the artificial neural network. A convolutional neural network is a type of deep learning neural network architecture commonly used in computer vision. In the realm of machine learning, artificial neural networks demonstrate impressive performance and finds application in diverse datasets such as images, audio, and text. Recurrent neural networks, particularly long short-term memory networks, are utilized for predicting word sequences. CNNs represent a significant leap in image processing capabilities, surpassing traditional methods. Improved hardware, parallel processing, and specialized GPUs have accelerated the training and deployment of CNNs. CNNs stand out for their prowess in image processing, marking a substantial advancement beyond traditional methods. Their superior capabilities are fueled by improved hardware, parallel processing, and specialized GPUs, accelerating the training and deployment of these neural networks in diverse datasets encompassing images, audio, and text within the realm of machine learning. While the artificial neural networks have just the input layer, the hidden layer, and the output layer, the convolutional neural network models have the input layer, a convolutional layer, followed by the pooling layer, and then a fully connected layer, and the output layer. Let's now see why CNN is used for computer vision. CNNs address challenges such as variability in lighting conditions, viewpoint changes, and occlusions. Some of the features of CNN that makes it suitable are local receptive fields, weight sharing, and pooling layers. Convolutional layers in CNN focus on small local regions of the input image. This helps the network capture local patterns and features, making it more robust to variations caused by changes in lighting conditions and viewpoints. This means whether the picture is taken in light or dark, that is nothing but changes in lighting conditions, or whether the picture is taken from one position and the camera is moved to another viewpoint, it is going to be invariant. Similarly, the same set of filter weights is used across different spatial locations in the input. This allows the network to learn common features regardless of their position in the image, making it less sensitive to changes in viewpoint. Pooling layer. The pooling layers are used to downsample the spatial dimensions of the feature maps, reducing sensitivity to small variations in location. There are two pooling features. One is max pooling, another one is average pooling. Max pooling, for example, retains the most important features in a local region, helping the network become invariant to slight translations and distortions. So the three features, local receptive fields, weight sharing, and pooling layers, help in obtaining features which are invariant to rotational, translational, occlusion, and viewpoint changes. In addition to the features just discussed like local receptive fields, weight sharing, and pooling layers, the feature hierarchies feature enables CNNs to form hierarchies of features where early layers capture low-level features to detect edge features and texture features, and deeper layers capture increasingly complex and abstract features. This hierarchical representation allows the network to recognize objects and patterns at different scales and orientations. The transfer learning feature of CNN involves pre-training a CNN on a large dataset and then fine-tuning it for a specific task. The knowledge gained from the pre-training phase helps the network generalize better to new datasets and variations in lighting viewpoints and occlusions. The ensemble methods combine the predictions of multiple CNN models, either trained on different subsets of data or using different architectures that can enhance robustness. The feature hierarchies organize low to high level features aiding object recognition at various scales. The transfer learning feature pre-trains CNNs for broad insights, fine-tuning for specific tasks, and the ensemble methods strengthen CNNs by combining predictions from diverse models, enhancing robustness and Let's now look at an overview of neural networks. Neural networks are a fundamental component of machine learning and artificial intelligence. They are computational models inspired by the structure and functioning of the human brain, designed to recognize patterns, make decisions, and perform tasks. The neural network architecture involves neurons, which are interconnected nodes, which are also called as artificial neurons. Each neuron receives input, processes it using a mathematical function, and produces an output. Figure 6 shows a sample neuron structure. Neurons are organized into layers: an input layer, one or more hidden layers, and an output layer. The input layer receives initial data, the hidden layer processes information, and the output layer produces the final result. So, neural networks are the backbone of artificial intelligence, mimicking the brain's structure. It can be thought of as interconnected nodes, and each neuron processes input, creating a network of layers. Input layer receives data, hidden layer processes it, and the output layer delivers the results. It's a digital brain making decisions and recognizing patterns. As we know, the neural network consists of three layers. They are input layer, hidden layers, and output layer. The neurons in the input layer represent features of the input data. Each neuron corresponds to a feature and the values represent the input data. In the hidden layers, they form the intermediate layers between the input and output layers. Each neuron in the hidden layer processes information based on weights and biases, and the output layer produces a final result or prediction. The number of neurons in the output layer depends on the task, whether it is a binary classification or a multi-class classification or a regression. Classification is based on categorical data while regression is based on a numerical data. So in the neural network's anatomy, the input layer captures data features through neurons. Hidden layers, which are sandwiched between input and output, process the information using weights and biases. The output layer delivers the final prediction. Neuron count varies for tasks like classification or regression. We know that the hidden layer, which is sandwiched between the input and output layer, processes the information using the weights and biases. So the weights are nothing but the strength of the connection. So connections between neurons have associated weights that determine the strength of the connection. Weights are adjusted during training to optimize the network's performance. Biases, these are neurons which have output non-zero values even when the inputs are zero. So biases are adjusted during training to fine tune the network. So in the neural network CNN, weights in a neural network are the strength of the connections between neurons, fine tuned during training for optimal performance, and biases are like baseline, enabling neurons to output non-zero values even with zero inputs, which helps in fine tuning during the training process. Having seen about the layers and connections in a neural network, next is the activation function. Each neuron applies an activation function to its input, determining its output. The common activation functions include sigmoid hyperbolic tangent function, which is called tanh, and rectified linear unit, which is called RELU. Next is the training, which involves backpropagation and loss function. Neural networks learn from data through a process called backpropagation. During training, the network makes predictions and the error is calculated. The error is then propagated backward, adjusting weights and biases to minimize errors. Loss function. This measures the difference between the predicted output and the actual target output. The goal is to minimize the loss function during training. Activation function defines a neuron's output in a neural network like a decision making tool. Popular functions include sigmoid, tanh, and ReLU. Training involves backpropagation and learning from errors. The network predicts, measures error, then adjusts weights and biases. The ultimate aim is to minimize the difference between the predicted output and the actual output, which is called the loss function. So let's now summarize what we have seen in this video. We have seen about an introduction to computer vision, its role in image processing, the role of convolutional neural networks in image processing, and the architecture of convolutional neural networks. In conclusion, we have embarked on a journey from pixels to predictions, unraveling the transformative role of convolutional neural networks in the computer vision, the first part. From understanding the basics to exploring their applications, this is just the beginning. Stay tuned for our next video on convolutional neural networks, an example where we dive into practical scenarios witnessing the true might of CNNs. Thanks for joining. The visual frontier awaits. See you in the next video.